Welcome to the 5th video in rotation and torque. In this video, we'll be having a chat about torque. So torque is often called the twisting force, and this is very nearly the correct definition, but not quite. So the torque is the rotational equivalent of a linear force, but it is not a force. The torque is a measure of how much a force causes an object to rotate. Another way of thinking about the torque is as yet another relationship between the linear and the angular variables. So the torque is something like the angular result of the application of a linear force to an object that can rotate. And for an object to be undergoing rotation, it needs to have a rotational axis. And as it turns out, we encounter torque multiple times every day. So every time we open any sort of door, we are applying torque to the door. So we'll use the example of a door to derive all of our expressions related to torque. So in this image, we have a grey door. It's fixed at one end with its hinge, so that hinge is its axis of rotation, and it's got the handle at the other end. To open the door from its current position, we apply a force F. So we apply a force F straight in front of us, but that is at some angle to the door. And so when we apply this force shown, we know the door is going to move in a circular arc in the direction shown. And what we're interested in is how far the door will move along that arc, or in other words, how far the door will rotate around its hinge or around its axis of rotation. And this depends on two things. It depends on how much force is applied, but also on how far from that hinge or from that pivot point the force is applied. So the further away from the hinge we apply the force, the more it will cause our door to rotate, or the farther it will cause our door to open. So now we have a two-dimensional problem. We already know that when a force is applied, it's only the component of the force in the relevant direction that causes the object, in this case our door, to move. Okay, so first I'll define my axes. So I have one axis, which is R, in the radial direction, and I have the perpendicular axis, which is T, which I call the tangential direction. Then my force has two components, the radial component and the tangential component, and it's at an angle phi to my radial direction. We already know when a force is applied that only the component of the force in the relevant direction causes the object, so in this case our door, to move. So the next thing to do is to figure out which part of our force, whether it's the radial or the tangential part, will cause our door to move in the radial direction, so to have an angular displacement. So if we pull on the door in the radial direction, so we pull directly outwards along the radial vector r, the door won't open further or close further. So the component of interest for us is the tangential component. And from our diagram, we can see that that tangential component is equal to F sine phi. And we can then define our torque as the product of our radial vector r and our tangential component of the force. So that gives us that our torque is equal to R times F times sine phi. We can also look at it from a different perspective. So if we now have a look at the components of our distance R, we have this component that's perpendicular to our force, which is called the moment arm. We can also define the torque then as the product of this moment arm with the original force vector. And that moment arm is by geometry equal to R sine phi, which again gives us that our torque is equal to Rf times sine phi. So we have the magnitude of our torque is equal to Rf times sine phi, and so we need to find the direction. And if you remember from our previous video, when we were talking about the direction of rotational vectors, the direction did not give us the direction of movement, but rather the direction of the rotational axis. So our torque is equal to R times F sine theta. And we know from our investigations into the cross product in the very first video that that is exactly the definition of the cross product. So our torque is equal to R cross F. And that means we can use the right-hand rule that we use for the cross product to find the direction of our torque. So in this case, we point the fingers of our right hand in the direction of R and we curl them towards the direction of F. And the direction our thumb is pointing is the direction of our torque. So in this example, our torque has a direction out of the page towards us. The final question that remains for us now then, we know how to calculate the magnitude of the torque, we know how to find its direction. is what happens when we have more than one force applied. So in the case where we apply more than one force to the door, so for example, if we have 3 siblings having an argument and one wants the door closed and 2 want the door open, we treat it as we would any force problem. So we know that the total force, or the net force acting on the system, is equal to the sum of all of the forces acting. We also know that the torque is equal to R cross F, or RF sine phi. And so for each force applied, there is a corresponding torque. And to find the net torque, all we need to do is to add each of the torques from each of the forces. So in other words, torque also obeys the superposition principle.